OSIsoft is pleased to have the opportunity to present as a sponsor of the SigmaFine Virtual Summit. SigmaFine and OSIsoft have been partners for a long time, and PIMSoft is an OSIsoft premier partner, a system integrator, and an OEM partner. I'd like to introduce to you Bernard Morneau of PIMSoft and Gopal of OSIsoft. And just to get started, what inspired the two of you to make this presentation together about data quality? Bernard?
Well, thank you, John, for the introduction. Gopal and I have been on this topic for quite a few years because we were colleagues at OSIsoft, and we've continued to discuss about this on a regular basis. And every year we have the summit, and we always wonder how can we deliver a message where both the PI system and SigmaFine from PIMSoft are complementary to each other, and how we complement each other from the perspective of improving data quality for our customers. So this year we kind of decided let's try to do this joint presentation and see if we can demystify that topic and take away any of the confusion that may be in people's head about this, the role of PI and the role of SigmaFine when it comes to data quality.
Thank you. And Gopal, would you like to introduce yourself?
Yes, hi. Again, Bernard, thanks for the opportunity. My name is Gopal, and I've been working with the PI system for 20 plus years. And I have been through multiple roles at OSI. Started out in software development, and then did some field services and tech support and product management, and then recently took on a role as a solutions architect. And in this role, I have been working with a lot of our partners, including common partners that we have with PIMSoft, and also a lot of customers who also use PIMSoft for the SigmaFine kind of applications. So with that, let me bring up the slide deck, and we will talk through some introductory comments we want to make. All right, so the topic we are going to talk about is industrial IoT time series data engineering. And time series data engineering is a much more broader topic, and it is really a catch-all umbrella for the data engineering, and data engineering as a prerequisite to anything that you want to do with the data after the data collection. So you have raw data coming, but the raw data is seldom useful as is. There are some uses for the raw data, but in a lot of cases, in some way, you need to make sure that the data that you're collecting from the sensors, you can trust the data. So that brings us to this data quality question. And many of you are already familiar with this topic, so we won't restate the problem of data quality other than to present the solution in the way we want to think about it from a PI system standpoint, and where PI system is step number one for the data collection. I have presented the summary here just for the sake of completeness, and I also have given you a hyperlink here if you want to get some more information on the things we're going to present here. I always want to start with my concluding slide. So if you don't remember anything, at least you know what the takeaways are. So let me start there. In this, we are talking about a layered approach to analytics. So I'm going to talk about the what and how of this layered approach. And as I mentioned previously, a lot of this is really, really useful as we come into analytics, and even more so with this machine learning kind of analytics, where the data really needs to be trusted data before you trust the results that are coming out of any machine learning, data science, or any advanced analytics you may do. Now, the data quality piece itself is a much larger part of a bigger presentation, because we use the same layered approach for talking about maintenance and the business initiatives that you have in maintenance. And there, the layers are slightly different. We talk about usage-based maintenance, reactive maintenance, predictive maintenance. So the layers are different, but the layered approach still helps you use fit for purpose data quality approaches to make sure the data you're feeding in is good, and then you can trust the results. And we again take the same layered approach when you start to look at process diagnostics, and again, as you apply machine learning algorithms to the processes. Now, we won't talk about maintenance and process related topics in this session, but I have given you links so that after the session you can go back and look at it. And let's just focus on just data quality here. So what do we mean by data quality when it comes to a layered approach and the Pi system? A picture is worth 1,000 words. So let me start, giving you a more of a pictorial representation of this data quality. Most of you are familiar with the data collection piece within Pi, and there we expose a lot of metrics as the data is being collected. Those metrics can be monitored, and we have an out-of-the-box tool within Pi itself called Pi Systems Monitoring. And the kinds of things that we are monitoring on it is, whether the CPU is getting used too much, or you are running low on disk, or how do the different modules within Pi, the interface data collection, or the analyses, the number of analyses that you're running, the buffers that are on the Pi system, how are they doing at a system level? And we call them health metrics. Anything that we do in data quality, and you're going to see those coming up here, but this is really a prerequisite to make sure that at a system level, things are working, and we make all those things available to you as part of the Pi system itself. There is some configuration involved, but it's very easy to do. So highly recommend, if you're not already doing it, to start looking at this Pi systems monitoring. We're going to now climb the ladder on this layered approach. So the easiest thing to do is at an individual sensor level. And you can easily find out if the data that you're getting is out of range. And Pi already has ways to do it. If it exceeds the instrumentation limits, 0 and a span, we put an out of range marker on it. Or if for some reason the control system is not reporting the data, we put an IO timeout on it. So all these items you need to figure out how you're going to incorporate when you're feeding it into some advanced analytics module. And we will talk more about it in a minute. The next level after the individual sensor is more than just one sensor, but you're now still talking about maybe just a single equipment, maybe a pump or a motor, and you have a few sensors, maybe half a dozen sensors. You can do some simple analytics at this individual equipment level to make sure that the data that is coming in is consistent. And we will step into that, and I will show you some details. And the next level of complexity or advancement that you can do is where you look at a number of equipment. So this is, in the industry, we call it the functional equipment group. So it is multiple equipment and could be typically hundreds of sensors. And here it could be some of the sensors are monitored sensors, some are really controlling sensors that you have. Regardless, you can apply some advanced analytics at this level, at this scope, to figure out what sensor is not reporting the numbers correctly. In some sense, you can also apply some machine learning modules at this level also, and we will step into that in a minute. And then the ultimate in the data quality piece is where now you're incorporating a connectivity model or a flow model in the way you're doing the calculations, including some mass and heat balance. And you are able to do that because there are some redundant measurements at this level. And so we are talking about an entire process unit, maybe even an entire plant. So this is multiple equipment group where you are bringing in really some of the sigma fine kind of calculations into the equation, and you are conditioning the data to make sure now the data can be used for this machine learning kind of modules or any other thing that you may want to do. Bernard, do you want to say anything more at this level?
Thank you, Gopal. Yes, I would say perhaps that, as technology advanced in the last couple of years, we've actually seen cases where, what we're doing at the multiple equipment groups level has been applied at some of the functional equipment group when, especially, I think is the case I'm going to talk about today is a case where, we can use the Sigma Find to infer some measurements which are not measurable, like enthalpies and things like that. And we can make some contribution at the functional equipment group level. Also because of the fact that, traditionally these large models with thousands of sensors, they would run on an hourly basis or daily or something like this. But, with the advance in computing technology, with advance in, the data collection systems and the fact that more and more things are connected and we have less and less dependency on manual entries, we're able to actually run these more sophisticated models every 15 minutes, every 10 minutes, and so on and so forth. So it's kind of becoming a gray area between process units, which are multiple equipment groups, and single equipment groups. So this is an evolution of how SigmaFind has been used in recent years.
So just to give you a little bit more on the spy system health monitoring, I'm just bringing up the kinds of things that are available out of the box. And you can see all these are template driven, and we make this available. So you can, at the links that I showed you and the documentation that I showed you, we give you the way you would want to monitor things at a system level, the AF server, the analysis service, the buffer system, and all that, plus a bunch of calculations that we do. So these are all the analytics, and all these analyses are also available as templates that you can just import and deploy. There is some configuration in place that you need to do, but you don't have to kind of redo or rethink all these calculations. The archive corruption, the compression ratio, the event queue duration. You can see, we are really trying to get a handle on the data collection piece and making sure that the data that you're expecting to come across from the control system or from an IoT device is really coming through. And then once this is in place, we can start looking at the numbers that are coming. So to give you a little bit more color to this gives you a feel for the kind of reporting that we have. So this is one of the screens available to monitor the different processes as part of the spy systems monitoring. This is like a level 0 of this layered approach. Read cache, archive, queues, write cache, the overall status, ping level, bandwidth, network speed, all at a system level. Now here is another one at individual server level. So this is the PyVision server or the RT report server. And we are just giving you metrics, and all these are, you just click on it and kind of drill down to get more details. So this number is yellow because we have told the system to flag us whenever the disk space gets to less than 50%. And then you can click on it to see using a file explorer or something to see what files are, or what is the large file contribution to this disk space. Same thing we do for if for some reason the CPU kind of maxes out at 100%, you can see what system services are contributing to those CPU usage, right? And make immediate corrections instead of having to get bad data and try to fix it just when you're starting to use the data. So now we are climbing up the ladder, and we are now starting to look at just a single sensor. And there again, we have simple analytics that we can do to tell you whether the control system is indeed sending the same data over and over. Sometimes the control system is kind of known to do that. The sensor would get stuck, and we call that like stale data, or the data has not updated in a long time, right? So that is stale data. And another case is that same stale data, we can also detect that it is kind of flatlined either at a stuck level or sometimes it is at a zero level, it'll get stuck. When you look at a trend, we call it a flat line because that is what the trend kind of looks like. And if the sensor is reporting, let's say every minute, you will see it as flat line for the past hour, right? And we want to be able to capture those kinds of bad data quality right at the source level. So you can set up the period over which you want to make sure you don't get into this bad data quality. You can set them up and the system will automatically notify you and tell you which tags and which streams have gotten into that kind of a situation. Bernard and John, any questions on this?
No, I think it's very important that our customers, whatever the applications, implement this fundamental discipline, and I think that's an important part of the message we're trying to deliver today in terms of data quality.
Would you know, Bernard, if your users are taking advantage of the spy system monitoring that I just mentioned in the last slide, or this may be really useful if they have not installed?
No, we don't have visibility typically into the PI system monitoring itself, but I think it's a very good, consideration overall because it's kind of even more fundamental than the tag by tag, data validation. If your PI system is not healthy, it could be compromising the data quality at the level where, it's not even actionable at the data level. So I think it's a good suggestion, and I think it would be welcomed by most of our SigmaFind customers.
And Gopal, I'm looking at these calculations for establishing whether a data stream is healthy or unhealthy. But I've got thousands or tens of thousands or 100,000s, maybe millions of tags. So how do I apply this to so many tags?
So typically we do this at an interface level, and you can define important tags, and we call them watchdog tags. And we typically use that as an indicator of whether or not an interface is healthy or not.
Thinking more on the level that you're showing here with the individual tag quality.
Yeah, so could be the problem is a little bit more involved. I mentioned this because you can use watchdog tag to do it, but we also have other capabilities because sometimes, let's say, you are trying to do some averaging or doing some totalization on some number, right? What you want to make sure that 50% of your data is not bad, right? You are willing to maybe tolerate, 5% bad quality data. So on top of some of the calculations and unhealthy that I've talked about here, there are also additional functions available. We call that a percent good function, and you can apply that to the averaging or some of the aggregations that you're trying to do. Were you thinking of anything else?
I was thinking of the ability to apply the same calculation to if you need to check a large number of individual tags. So I appreciate that if you take a sample of tags from a particular data source, then that's a pretty good indication that that data source is functioning properly. But there's still some tags you're going to want to check the individual tag to make sure that it's not stale or flatlining or having bad quality. And I'm just looking at this and I'm saying, if I've got to apply this to thousands of tags, that looks like a lot of work.
Not at a template level, because these calculations are deployed using templates. So as long as you stick to a template-based deployment, it is not a tedious task.
All right, that's what I was trying to get to. Thank you.
Yeah, but you brought up an important point, and actually it kind of tees it up to the next layer that I'm talking about, where when you want to move beyond a single tag, right? There are ways, because most of the time in a process and in an equipment, the tags in an equipment, whether it is a pressure or temperature or amperage or vibration, whatever, they're all kind of correlated. And we can use the physics of that relationship to come back and tell you, that some sensor is not reporting the right value. So, typically this is what we have done. Like on a chiller, I typically use a kilowatt per ton as a metric. I get the BTUs that are the chiller is putting out, and I know the kilowatt consumption. So it is a simple calculation for me to do a kilowatt per ton. Or on a pump, instead of individually looking at the pressure and the flow, I do a combined head flow calculation and use that as a metric. And this doesn't have to be just bivariate. You can apply it to even at a system level. So that is really the next level of complication at the next rung of the ladder. But basically, the head flow and the kilowatt per ton kind of a usage, this is the manifestation of it. So the thing that you're looking at on the solid head flow curve, that is the vendor supplied head flow curve for this pump, and I know what the expected relationship is, right? And this is what I'm actually getting. But I do have this one point where the pressure value that I got is is a bad number. I mean, that is why it is coming in, sitting out like this. And it is easy for me to make sure that I can eliminate that number from whatever downstream calculations that I'm going to be doing. So we suggest that when you go beyond a single sensor, you start now, bringing in and using some physics kind of equations to look at 2, 3, 4 sensors in a joint manner. So that is another easy way for you to tackle this bad data quality when one sensor out of these 2 sensors or 3 or 4 sensors is reporting bad numbers. And you can use the same logic at the next level. So now we are talking functional equipment group. So we are talking, tens or hundreds of sensors, and the task becomes a little tedious when it goes to 15 sensors and 20 sensors or hundreds of sensors, where now you would bring in some machine learning kind of logic to get a handle on it. And it is kind of easy to illustrate this using a practical example. So I'm using an air handler example here. Now, the air handler is part of a building management system. Typical view of a air handling system is right here. This is the air handling unit. And these are all the different rooms that you can think of. This is the corridor. And this is the cold air or hot air from the air handling unit that is going into these. These are the volumetric supplies into these rooms across the corridors. And the system that we are trying to analyze is all the sensors that we have here, the supply air temperature, the outdoor air, the damper position, the return air temperature, the chilled water loop, the temperatures there, the supply fan constraints. So now we are looking at really, tens and 15s and 20 different sensors. How do I know if one or more sensor is not giving me the right numbers? And an easy way to do that is to take advantage of system level correlations you have among these sensors, but we bring in machine learning logic to do this anomaly detection. And let me just give you the results. The machine learning algorithm itself is typically done outside of Pi, but we make that data available. And what comes out of that machine learning logic is really a transformation equation that you can deploy back into Pi. So that is the cooling coil output temperature. And it says that I need to transform the data in this way. So I know multiply it by this number and divide by this number. So it just gives me an equation. So essentially what I've done is taken this multivariate problem, and this doesn't need to be limited by 6 or 10 that you're looking. It could be 15, 20 items, but this machine learning algorithm will know how to reduce the dimensions on it and take advantage of all the correlations among the various sensors. And it is doing it strictly at a statistical level and strictly at a data level, but it is a reliable metric. So what we have done here is taken this multivariate problem and reduced it to 2 dimensions, and the module itself is called principal component analysis. And you can see here, I'm doing a plotting of all the data on a 2-dimensional plot. I'm still using PyVision as my plotting mechanism. And all the blue items are what I had used when I was doing the model development. So that becomes like the backdrop. And the yellow items are what is being calculated in real time. Every 5 minutes, every minute, I can do that transformed equation calculations. I can plot it. And whatever is outside of this region, and this is all being done in a statistically robust way. So anything that comes out, that is a possible indication of an anomaly or a suspect reading. And we also tell you which sensor is contributing to that anomaly, right? And there is another way to look at it, like we are not expecting you to be staring at these screens. I typically go and link in a Pi notification to it where if it exceeds some thresholds that I've given, or I watch the rate of change on it, I send a notification with an embedded link that you can click on and bring up the screen. So we are trying to make use of all the capabilities within Pi to catch the bad sensor quality as they begin to happen and for you to take corrective actions. And immediately you can also look at all the other sensors that are contributing it, and you can pick and zoom into it. But that is really a longer talk. And I've given you the links to it if you want to study this in more detail. So now we come to the last rung on the ladder where I will now yield to Bernard for him to talk through some of the SigmaFine plugin capabilities in this.
Thank you, Gopal, for walking us through that, or having us climb that ladder. And as you said, the last rung of the ladder is something that we at PIMSoft, with our SigmaFine solution, are more familiar with, and it complements Pi system, we think, very well. I mean, at that level, like you said, we're looking at groups of equipments, and what we're basically doing is we're taking advantage of a lot of spatial and temporal redundancy in the data by having more measurements and by looking at larger periods of time, and we are applying constraints. The classic ones are, mass or energy, but also we can look at volume, we can look at composition, and we can look combined mass and energy or heat balances. So this is forcing essentially out of the data a reevaluation of each measurements to a more statistically accurate value, and then it's driving the reduction of the variance overall in the process. The way we talk about it, in our world is a little bit different. We see it as a life cycle management when it comes to data quality. I mean, we're always with SigmaFine, we're always sitting at the end of the process where people are asking data to be presented in a certain way to them, which is why we use sometimes the term conditioning, because conditioning embeds validation, reconciliation, and everything. Because conditioning is a concept where you're conditioning something towards a certain end use or towards a certain set point or towards a certain specific situation. So in order to get there, we do need that our customers apply some lifecycle management on their raw data, and that's where the Pi system comes in. And a lot of what you've explained, especially in the first two rung of the ladder, is about minimizing errors and maximizing the quality of the data, and it's done without necessarily the knowledge of how the data is going to be used. So a lot of it happens at real time, as you mentioned. A lot of it happens not long after the data is collected, and some of it may happen around certain specific equipment, which are very well defined and have good models or good equations or good physics that we know of that we can apply. So from a PIMSoft perspective, the life cycle management of data is very important, because if we don't do it, it really limits the ability of SigmaFine to perform in terms of delivering the desired data set to the end users. I'll bring up a classic example, which is something that, like I said, in recent years, we have been doing a lot of, is basically looking at an equipment group that is rather complex, that has enough spatial and temporal redundancy in its measurements that we can apply SigmaFine, and increasing or reducing the resolution. In other words, going from an hourly to every 15 minutes or every half hour or every 10 minutes when we can. So the case here is one of a furnace where we're trying to improve the combustion efficiency. And basically what we're trying to understand is all the variables that would eventually impact the excess O2 in the flue and see how close we can get to the desired target. So the exercise is very simple. It's like a before and after kind of thing. When you look at the before, this is data as measured. So we take the data out of the PI system and we just try to run our analysis. Then presumably, this may be a case where some of the data may not have been cleansed, or some of the techniques that we've presented through Gopal's presentation today may not have been applied. So it doesn't look so good. But in general, I would say most situation, when you look at data, it may not be as bad as this one, but it's not necessarily in a readily usable case for a variety of reasons. So if we take the data set from the left-hand side and we create the model, bring it into SigmaFine, bring the data into the SigmaFine, apply a certain, a good amount of temporal redundancy. Each data point there represents a run. So these runs are, let's assume they're 15 minutes in this case. So you've got a few days of information built into that chart there. And then by applying, basic mass and energy balance, by applying some basic thermodynamics, this is a crude furnace, by the way. So we're having, vapor liquid equilibrium calculations and everything we need, every capability from a thermodynamics or physics standpoint, or every aspect of the product properties that we can leverage into the model, we bring it in. And you can see that once we do that, without applying any kind of additional data analysis techniques, we're just using data as measured and applying engineering principles and a bit of statistics, that we're coming to something that is a lot better in terms of being usable. So in addition, in this case, for example, it's not shown here, but this was done also considering the different crudes being run. So we were able to generate one of these curves for every crude types as well through this process. So over time, we're getting a very good way, very reliable way to manage and control the efficiency of that furnace using just simple SigmaFine application. So that's a typical example of what we do using SigmaFine. Which brings me to the point that, when we talk about data quality, what we often try to explain to a lot of our customers is that if you don't pay attention to your data quality, you don't take any action, whether it's at the PI system level or whether it's at the SigmaFine level, it doesn't really matter. It's just data quality is a way of life. It should be a way of life in process industries. You're unavoidably creating some downside financial losses somewhere. You're missing on something somewhere. And I think Gopal has given you some examples. I've given you an example. So if you don't have a good discipline of data quality, or if you don't have a data quality practice in your organization, there's a loss. Often that loss is being ignored or is not visible. I mean, what we don't know doesn't hurt us. But essentially it's there, and it's been proven case after case that the reality of most process plants is that data needs attention. Now, when you start to bring it attention at the beginning, it's kind of overwhelming. And John was making the point, like, how do you track 10,000 points, for data quality on a day-to-day basis and stay on top of your game? It's not an easy thing, but there are good ways, good practices in the PI system, and there's methods out there that we can use to scale that up. But once you scale that up, you really are getting into a new phase. And this phase now is, it used to be before digital transformation, there was like a trust building phase where we had to, users had to be convinced that data was good. They were coming in with the assumption that data is no good. But now today it's not an option. With digital transformation, if you give it bad data, you're going to get bad results. So data quality is become a mandatory practice in a lot of applications today in the industry. And that's why, in the SigmaFine world, we say transforming data into digital assets is very important, because digital assets is what everybody's talking about. And digital assets is the fact that we can produce something that is digital and is considered usable to drive economic value. That's what gives it the qualifier of being an asset. That's what creates upside financial gain. So I always explain to our customers that, in data quality and in relation to sigma fine or pi, I mean, the benefits are, you have a double-sided benefit equation, which is really a win-win on both sides. I mean, preventing loss due to bad data and also driving improvements because you're having better condition data to work with. And something we have also to realize is that we are living in a world of real-time data, and sensors can get dirty, can fail. So if we don't apply this data quality practice every day, I mean, eventually, even if we succeed temporarily, the data quality is going to go down again. So this is an everyday practice that everyone should have in the industry. I don't know, Gopal, if you'd like to comment on this from your perspective.
Yeah, I want to go back to the scaling issue that you talked about and John brought up. Now, it is very common to see within Pi systems the number of calculations that we handle. So you may have 10,000 streams or 10,000 sensor thing, but it is perfectly fine for me to do 50,000 calculations on it. So even if I'm tracking every tag separately and making sure that it is not flatlining, the Pi system is able to handle it, and I can horizontally scale those calculations. In fact, I was just on another conference where the customer was talking about running literally hundreds of thousands of these AF analyses kind of calculations where you're trying to do something with the raw data and putting it through the analytics and doing something else after the analytics. So it is fairly okay to do hundreds and thousands of these AF kind of analytics, all handled by the Pi system.
Thank you. Yeah. Another aspect also from a sigma fine performance, our performance is limited by the quality of data. So being able to scale these calculations is very important, and is something that one of the reasons why sigma fine is built on AF in the first place. So thank you. Just wrapping up as a conclusion from my end, different than Gopal, he put his conclusion first and put mine last. Something I'd like to share with you, which is we haven't talked about, but the first part, I think the direct benefit of model-based data validation, I think you're all sold on that. And we just gave you tons of reasons for recognizing this as a benefit. But something that is really an indirect benefit of data conditioning, by introducing a model and connectivity and introducing constraints, you're basically able to use the residuals. In other words, the difference between your measured values and your predicted values, and use that as an indicator to go back and troubleshoot your metering systems. And that's super important in many cases, because one aspect of using something like SigmaFine is to create a certain data set that's usable by the business or usable by people or other systems. But another aspect of it is to actually understand the level of quality of that data set and being able to take actions to improve it further. And the only ways you can know how to improve it is if you understand where the discrepancies are. So it's not often mentioned, but SigmaFine is a very powerful tool when it comes to understanding the residuals between those measurements and the estimated value, because they're driving you to the maintenance of your meters. They're driving you to understand maybe if you have a certain aspect of your process lined up properly, you're missing some information, you missed some transfers and things like that. So it's a very efficient tool to detect other errors or other potential data issues that are not necessarily related to the signal themselves, that are related to the equipment and everything surrounding those signals. And something as well that is more soft as a benefit, but when you're compiling into a model with connectivity and with all the equations and all the analysis rules, you're compiling all your knowledge about a certain process unit. You're basically putting that knowledge in a digital form that is now making it reusable by a lot of people in the organization. So you're taking it out of a spreadsheet, and you're putting it into an environment like AF, and you're essentially making it reusable for other applications, but you also are preserving it. So if you're in a aging workforce situation, that's also a very, it's not a hard benefit, but it's a very substantial benefit in many cases. The fact that you have the discipline of creating these models, maintaining them, and running them on a day-to-day basis it will keep you on top of your game day after day. So that's what that brings us to an end. I don't know, Gopal, if you'd like to make some further comments before we go to.
Yeah, I think we can open it up to questions. John, if you had any.
Yeah, I just think that Bernard made a very important comment about the ability of looking at the actual versus the predicted results of the model. And if you can store those two values historically and compare them to each other, I think it gives you the opportunity to go back and analyze the accuracy and efficiency of your model and to use that as a training tool for your model. Correct me if I'm wrong, please, Bernard.
No, that's correct. I mean, the end game is to have as good quality as you can, but you don't achieve this on day one. But if you use the residuals, you can win the war by winning very small battles every day and making sure your instrumentation is always in good shape and things like that. And there's lots of money also involved in doing what we call condition-based kind of maintenance for instrumentation, because you can even save money from a maintenance standpoint by being able to pinpoint which meters are not performing well on any given day versus being on a schedule-based maintenance for meters. And these meters have a big impact business-wise as well, because not only there's a maintenance cost, but there's also the impact of all the decisions that are made, because of the fact that that you have a certain quantity of product in inventory, then that will drive the supply chain or drive your shipments or your sales. There's a lot of ramifications that are involved there, which if you get it right, you get a big reward all the way through.
And so many sensors are enabled with HART protocol, and the HART has self-diagnostic information about those meters, but I don't think a lot of people are actually exploiting that self-diagnostic data that could go straight from the meter into a Pi system and then be analyzed by SigmaFine.
Exactly. And then, I mean, you're making a good point. I mean, when you have these very smart meters, it's great, and you should take advantage of them. But when you throw SigmaFine on top of this, basically you're able to have an economic measure of the significance of the impact of the defect or the lack of performance of a certain meter. So there's a big question of prioritization of which instrument or which meter you can repair or clean or recalibrate, and also even in some cases which meter you should be installing in order to improve the overall accuracy or to reduce the overall variance of your data set. When we're talking about losses, and things like this, that becomes super important in the end.
Maybe, John, I will include a reference to the NEMO standards in the link, in one of the links that we provide for data collection from these smart meters, who the meter itself kind of announces when the sensor is getting bad or there's a drift in the sensor, and you can collect that right from the sensor at a sensor level. So I think that'll be useful. Okay, so we are kind of past our recording time, so I'll kind of stop the recording for now.
One other thing, though, I'd like to comment on Bernard's. I mean, if your editors can fix this up.
Yes, we can fix this up after. Yeah.
So I'd like to make one more observation about the difference between actual and predicted, is that becomes, I think, another layer in Gopal's staircase of layers of analytics, and that you're using that to, now we're past analyzing the sensor data, and now we're analyzing the data quality of the model itself. So I think it's a whole other level on the staircase.
Yeah, sometimes I refer to this as sort of a feedback loop, that we get basically by using SigmaFine. You're able to feed back into the measurement systems, feedback into the Pi system, and helps troubleshoot. It's not a direct method like what you described. Yeah, you check every tag, but it's an indirect method of, feeding back to the system and understanding how the system performs. Definitely.
Yeah, John, now you're reaching the penthouse level for model correction. And that is true. And we do that. And I know both SigmaFine, and we also encourage people doing this machine learning models to write back to Pi so that there is a historical record of when the model is doing good and when the model is not predicting as well. So now we're not talking sensor quality, but now you're talking about model quality and model calibration, right? So that is a whole new set of use cases for conditioning.
Yeah, good. So which brings us to a step in your ladder, a hung in your ladder that is not there yet. So I guess that's a good place to stop our presentation. Gopal, I would like to thank you very much for taking the time to join us at our event, and John for taking the time to participate as well as a moderator for this discussion. We appreciate it. We appreciate it a lot, and I hope we can get a chance to redo the same thing over and over again in other venues and instances. So, guys, thank you very much. A pleasure working with you.
Thank you, Bernard, for having us at the SigmaFine Virtual Summit. We really appreciate the opportunity to sponsor and participate.
Thank you.